Good afternoon to you all, although perhaps a good morning to some of you joining us from other parts of Australia. Thank you very much for joining us. This is the Australian Geometric PDE seminar series. This year, I suppose, we're hoping to come to a fuller understanding of some of the exciting things that happen in Yang-Mills theory. In particular, we're hoping to eventually get a handle on some of the amazing work that Karen Uhlenbeck has done during her career. To start us off, it's my pleasure to introduce to you Max Orchard, who's currently a PhD student at the University of Queensland. Max has kindly agreed to run through some of the basic definitions and other topics that we're likely to see as we take our journey through Yang-Mills theory. So please take it away, Max.
Yes, thanks, Tim. So, thank you to the organizers, Tim, Glenn, and Paul, for giving me the opportunity to speak. Yes, and in the chat, it's a very happy International Women's Day to everyone as well. My name is Max Orchard, and I'll be running a brief, I'll be giving an introduction to the main objects that we'll be studying in Yang-Mills theory, and a little bit of the motivation behind why we're studying some of these things. So, at its core, Yang-Mills theory is something that we call a gauge theory. Now, a gauge theory is what we call a field theory. Now, a field theory, I'll get onto what that means a bit later, but a gauge theory is a field theory in which the Lagrangian of the system, which is something that encodes all of the dynamics of the system, is invariant under some sort of transformation of the system. Now, by transformation, I mean a smooth action by a Lie group. And essentially what this does is, well, the Lagrangian is something that encodes the dynamics, and it's invariant under a Lie group action. It basically encodes the symmetries in the dynamics of the system. Now, a gauge theory is a field theory, and a field is in the physics sense of a field. So basically, a field assigns to every point in some sort of space-time. You could think of it like that. Every point in space-time, some object from a collection of objects. Now, a very simple example is, let's say you just have a 2D plane. You can assign a temperature to each point on this plane, and this will give you a field, a scalar field, where at each point you get a temperature scalar. Now, you can also assign, let's say, an electric force vector at every point that describes how an electric charge, the force that would be imparted on this at every point. So you can also assign vectors, but you don't just have to assign like a scalar or a vector. You can really assign quite a lot of things. For example, a stress energy tensor, you can assign the phase of a certain electromagnetic wave. But the idea is at every point, we attach to it some sort of collection of objects, and we can pick a certain object in that collection to get a field. Now, the concept or the object that allows us to study this is called a fiber bundle. And study fiber bundles, and a field, which is an actual assignment of one of these objects to each point is what we call a section of this fiber bundle. Okay, so now we have our field theory. It's some sort of fiber bundle. We now need some sort of transformation to act on this field. And as I said before, this is going to be probably some sort of Lie group, and we're going to have a smooth action on it. So this transformation needs to act on the field so that at each point, we might get a different object from the collection of objects that is assigned at that point. However, we also need to have the same collection of objects. We can't change the collection of objects at each point. So we need a transformation to act on the field so that we can get a different object at each point. Now, we also need it to be from the same collection of objects, though. Now, what this means is that we need some sort of group action, as I said before, but it also needs to preserve the fibers of this fiber bundle because we want the collection of objects at each point to be the same. So, oh, that's a very weird need. We need a group action that preserves the fibers of our fiber bundle. And the object that does this is called a principal G bundle. And finally, we're also going to be talking about the dynamics of the system. So we somehow need a way to move some point to another point. And in a sense, look at the difference in the thing that we're assigning as the field. So the way that we do this is with something called a connection. We also need a way between points / fibers. And the object that we want to study is called a connection. Now, in this talk, my goal is to define all of these three objects, as well as provide some examples and maybe some properties of these objects. So yeah, the first thing that I'm going to talk about is fiber bundles. Okay. So definition. A fiber bundle. So I'm going to write a fiber bundle as a tuple. So it's just a collection of these objects, which I'm going to write as E, B, pi, and F. Now, we want E, B, and F to each be topological spaces. I'm not going to be getting into the smooth stuff just yet. So these are topological spaces. And we call these the total space for E. B is called the base space. And F is called the fiber, respectively. So we've defined what E, B, and F are. Pi is a map from the total space down to the base space. And this is a continuous surjection. And we call this the projection map. And finally, we want this fiber bundle to locally look like a product space. So explicitly, for every X in your base space, there exists some open neighborhood U of X that is contained in the base space, such that there exists a homeomorphism phi, which we're going to take from the preimage of U into the product of U and F, which are our fibers. And we also want this homeomorphism to sort of commute with our projections, in the sense that if we apply phi and then project onto our base space, this neighborhood of the base space, that's the same as just projecting down here. Now, I'll note that the preimage of U here will have the subspace topology in E. Such homeomorphisms, or such pairs of open neighborhood and homeomorphism, are what we call local trivializations. And if we look at the preimage of just a single point in our base space, we call this the fiber over the point X, and we denote it with E sub X, where E is the total space, and then we say that E sub X. Now, one thing that immediately follows is that all of the fibers over every point X is actually just homeomorphic to our fiber space. So I guess we don't really need to have this F in the tuple. So we often just denote a fiber bundle by pi going from E to B. So this map encodes all of the information in our fiber bundle. It encodes our total space, our base space, and the projection map, and we can recover what the fiber should be based on just looking at the preimage of a certain point in the base space. This is a very technical definition. I'm going to draw a bit of a picture to maybe explain what each of these conditions mean a bit better. So the setup here is we have a base space B, which is some topological space. We have some total space E, which is in black. And if I give you a point X on the base space, we have a map going from E to B. And if I draw some sort of line here, I'm going to denote this E sub X. This is the fiber over X. And every other point, or every point on this fiber, gets mapped down to X by our map pi. So this tells us the first two conditions. At every point, we're going to get some other fiber here. And the local trivialization condition basically says that at every point, we can find some neighborhood, some open neighborhood of our point X. I'm going to call this U, such that if we look at the pre-image of U, essentially all the fibers in the neighborhood U. If we look at the pre-image, which is all of this, that was U, basically, there exists a homeomorphism between this kind of a bit weird space with all these fibers in it, like this, into just a Cartesian product of U and F. So locally, topologically, we look like just a product space between the two. And of course, this is homeomorphic to F. Okay, so I'll go through some examples now. First example I want to go over is probably the most simple one. Fiber bundles have to locally look like a product, but what if globally we're a product? So we're going to set E to be B cross F for two topological spaces B and F. Now I'm going to define the projection map from E down to B. Now E, of course, is just the Cartesian product of B and F. So I'm going to send this just to be, well, the projection onto B. Now, this is clearly a continuous surjection, and in order to define a local trivialization, we can just set our open neighborhood to be all of B. We get not just a local trivialization, but a global trivialization given by just the identity. So this goes from the inverse image of, or the pre-image of U under pi, which you may notice is just all of E. And this goes to, by definition, U cross F, but U is just B. So this is just a local trivialization. It's a homeomorphism, obviously. And yeah, we look globally like a product space. So a fiber bundle of this form, so a fiber bundle that's just the product of two spaces, is what we call a trivial bundle. Okay, so let's do another example. I'm going to take the base space to be the circle. And I'm also going to take my fibers to be the unit interval 0, 1. Now, if we were looking at a trivial bundle, this would just be some sort of cylinder, right? We would get something that looks like this. So our base space would be this circle here. And yeah, this is what the trivial bundle between S1 and the unit interval would look like. So this is just this space here. Now, instead of just doing it in this trivial sense, I'm going to add a twist to the cylinder. And this gets you the Mobius strip. Now let's see if I can draw how I can draw this like this. Our base space is still just a circle. And we get our fibers that look like this at every point, just as we would for the trivial cylinder. And notice how locally, at every point, we look the same as the trivial bundle. So locally, we're trivial. So this is a fiber bundle. However, there's a twist here, which means that we are actually not globally the Cartesian product. We're only locally the Cartesian product. So this is non-trivial because there's a twist here. Now, of course, this is just the Mobius strip, quite a well-known example of a non-trivial fiber bundle over the circle. These have a special name, though, these fiber bundles where the base space is a circle. These are called circle bundles. And you can also talk about sphere bundles where the base space is some Sn as well. And finally, the last example I want to go over is one that's probably very familiar to everyone here. We're going to let the base space be some smooth manifold. And we're going to look at the tangent bundle. So this assigns to every point the tangent space at that point. So in general, this bundle is non-trivial. And an example of such a non-trivial bundle is if we take our base manifold to be the two-sphere, and you can see that this comes from the Hairy-Ball theorem. Now, picture here, I'm going to set blue to always be the base space here. S2 like this. And essentially at every point, we get this tangent space here. And what you may notice is that all the fibers here are vector spaces. And such a fiber bundle where all the fibers are vector spaces are called vector bundles. Is a vector bundle. I think circle and sphere bundles usually refer to the fiber rather than the base. That could be possible considering the vector bundles are when the fibers are vector spaces. So the last thing I wanted to quickly define before we get into G bundles is a section, because this is how we look at fields. So a section is simply a continuous map from our base space to our total space, such that if we look at f of x and then we project back down onto the base space, we just get x. So essentially, we map a point in the base space to a point in the fiber. The space of all sections defined on E is denoted with this capital gamma here. And I guess a picture here would be if we have our base space here, at every point we have a fiber that lies in our total space. F assigns every point to some point on the fiber, like this. Okay. Now, for example, if we look at a section of the tangent bundle, we are assigning to every point in our base space, which is our manifold, an element from the fiber, which is the tangent space. So we're assigning to every point a tangent vector. We get a vector field. Now, I will say that in general, it may be impossible to define a section globally on a fiber bundle. And we'll see an example of this later. So it might be impossible to define a global section on a fiber bundle. However, if we have some sort of local trivialization U defined on an open neighborhood U, then we can always define a section on U. And we call this a local section. Okay. Now let's move on to principal G bundles. Definition. So a principal G bundle is just a fiber bundle, but we have some sort of group acting on the fiber bundle that preserves the fibers. And there's also one other condition about the fibers actually being homeomorphic to the group itself. Let G be again, here, I'm just looking at the topological case. I'm not going to be going to the smooth case just yet.
Hey, Max.
Yes?
Just a little question. You can always have the projection being the trivial one, right? That just sends everything to the base point. So
what are you referring to, sorry?
I mean, about not being able to define a global section. I'm just a bit confused about what you meant. So for example, on S2, I could just assign all the zero vector field.
Yes, that is possible.
That's a global
it may
section.
not always be possible to define a global section. In fact, there's a proposition that we're going to cover later on that says a principal G bundle admits a global section if and only if it's trivial. So you could consider, for example, the frame bundle on such a on the sphere, and we know that because it's not parallelizable.
Oh, okay.
So that Glenn, the vector bundle always has a section, the zero section, as you just said.
Yeah.
But a principal bundle may not have.
Yeah, I understood after Max gave his example. Thanks, Pete.
Yes, and I will be giving this example actually a bit later on. So got a bit ahead of me there.
All right, cheers. No worries. All good.
Yes. So a principal G bundle. Oops, I'm still writing in shapes. Is a fiber bundle, which goes from, which has pi E and B. Together with a continuous group action of G, such that, well, first it preserves the fibers. So if Y is in a fiber, then if we act on it by any group element, we also stay in the fiber. Now, second, if we look at every fiber and every point in the fiber, if we fix those, the map that goes from our group to our fiber and sends G to YG is a homeomorphism. So essentially, our fibers are actually homeomorphic to G. Now, note that they won't necessarily have a group structure. We're not saying that this is some sort of group structure preserving map. We're only preserving the topology. So topologically, it's the same as G, but it may not have, for example, a distinguished identity element. And we also require the group action to be transitive and free on the fibers. And in this case, we call G the structure group. So let's give an example. And here, this example is going to be just the frame bundle of a vector bundle. So if we consider some sort of vector bundle, a frame at some point in our base space is, well, we can think of it as an ordered basis of this vector space, which is the fiber at X, or equivalently, we can say that a frame is a linear isomorphism P from Rn to the fiber. So this also defines an ordered basis for Ex by just looking at where the standard basis for Rn goes. So this is a frame for a vector bundle. Now, if we look at the space of all frames at a point X, which we're going to denote with F sub X, F for frame, this space has a continuous right action by GLN. And explicitly, the element G acts on a frame by, if we look at this new frame, it's simply just the composition of G with frame P. So this also goes from Rn to Ex. Now, this action is clearly transitive and free. This is just by linear algebra. And this map is also clearly a homeomorphism, and its inverse is just given by, or P compose G inverse. So we get this action here that preserves the fibers, is continuous, transitive, and free. If we take the disjoint union of each fx, we obtain something called the frame bundle. Which I'm going to denote with Fe, and it's just the disjoint union of all x in B of fx. Now, this is a principal GLN bundle with the action that I just described. And each of the fibers then is homeomorphic to GLN, which hopefully makes sense, morally makes sense. Now, another example, I'm going to take the base space to be the circle. And I'm going to have my total space look a little bit weird. It's like two circles on top of each other, but with some sort of twist here. Like this. So it's kind of like the boundary of the Mobius strip, if you want to think of it like that. And then pi maps from here down to the circle. Now, here there is a natural action by Z2 here on E. Basically, if you're the identity, you stay where you are. If you are not the identity, you basically move to the other side of the you move to the other side of the boundary, basically. Now, this defines a principal Z2 bundle. And what you may notice is that if we look at a certain point, I might do it with blue so I can be consistent with my colors. If we look at the fiber, we get these 2 points. We get something that's homeomorphic to Z2. So the fibers are homeomorphic to Z2. That's not really, it's like a discrete topology, but yeah. And I'll give one more example. We are going to take the trivial bundle, R4 cross the circle, or U1. Now, this is a principal U1 bundle. And if we want to just define an action on this, we can just define it by multiplication on the fiber itself. So if we act on an element of R4 cross U1 by some other element of U1, we just get multiplication. Now, what's special about this G bundle is this is actually the bundle where electromagnetism occurs. So the R4 here corresponds to space-time, and the U1 kind of corresponds to the phase of an electromagnetic wave kind of thing. So this is actually, where electromagnetism, the field theory of electromagnetism happens. Okay, now getting to what we were alluding to earlier, this proposition that states a principal G bundle is trivial, is a nice characterization of trivial principal bundles. If and only if it admits a global section. Now, this statement wouldn't be true in general if you just had a general fiber bundle, because as we said earlier, all vector bundles will always admit the zero section, which sends an element X to the zero vector in the fiber. And it will always admit this whether it is trivial or not. So you can't just use this characterization on any fiber bundle, but on principal G bundles, it does work. For example, the frame bundle that we just discussed earlier. Okay, so let's quickly verify this statement. So we'll define this to be a principal G bundle. And first, we're going to suppose that the bundle is trivial. If it's trivial, we have a homeomorphism from E to B cross G. That's what it means to be trivial. You're basically globally a product. We can define a global section on such a trivial bundle by just, I'm going to write S for section. We just send an element of our base space to the inverse here, along with our distinguished element of G, E. So basically, yeah, this defines a global section, a section that's defined globally on the trivial bundle. Now, conversely, suppose there's a trivial section, a global section. So the idea is that now we want to show that E has to be homeomorphic to B cross G. That will show us that we're trivial. And such a trivialization can be defined by, I'm actually going to write its inverse because that's a bit, well, it doesn't really matter, but I'm just going to write it like this. The inverse of the trivialization that goes the other way around. And we're going to send an element xg from our Cartesian product to S of xg. So this section is defined globally. We just send x to wherever the section takes us, and then we act on it by the group. And this is clearly continuous because we have a section which is continuous and the group action is continuous. It's a bijection because the action of G is free and transitive on the fibers. And also, the inverse can be a little bit harder to write down, but hopefully you believe that this is also continuous as well. I might just draw a picture here. And we have our base space B, our total space E, which is where our fibers live, a point X, and we have our fiber here, it's homeomorphic to G. So S is already defined here. And essentially for every Y in E, I should say Y in E sub X. For every Y in E sub X, there exists a unique element G that takes you there because the action is free and transitive. And this kind of describes the inverse. You can go backwards in this way. You can always go from Y to S of X, and then you can just go backwards like that. That defines your inverse. Okay, so that's basically wraps up my discussion for principal G bundles. And from now on, I'm actually going to take smooth G bundles. Now, what do I mean by a smooth G bundle? Well, I want B and E to be smooth manifolds. I want pi to be a smooth map. I want G to be a Lie group. And I also want the action to not only be continuous, but I want it to be smooth as well. And finally, I want these local trivializations that send your neighborhood of E, your pre-image of U, to your Cartesian product. I want these to be diffeomorphisms instead of just homeomorphisms. So we're just upgrading now to the smooth category by adding this additional structure. Okay. Now, we'll get to the final object that we're going to define in this talk. And now I'm going to define it in terms of, I'm hoping I'm pronouncing this right, the Arisman connection. There is an equivalent way to define it, which I'm going to talk about in my next talk. But for now, we're just going to look at Ehresmann connections because I think it's a bit more intuitive as to what's going on and what we're trying to achieve. So we're going to suppose that we have some smooth G bundle.
Sorry, could you write down that name, please, Arisman?
Oh, yes, I will write that. The name here is Arisman, like this. And we will define what an Arisman connection is a bit later on, once we've discussed a little bit more structure here. So we're going to have some smooth G bundle. So P, we're going to say P for principal. That's our total space. We're going to have some base manifold and then our smooth projection. Now, currently, you're probably well aware of this in the smooth manifold setting, that there isn't a way to naturally identify tangent spaces at two different points. And then the way that we do this, the way that we get around this is by adding an additional structure called a connection. Now, of course, on a Riemannian metric, with a Riemannian manifold, you have a distinguished connection. Here, we're not going to assume that we have any Riemannian metric a priori. We're just going to have smooth manifolds here. So to get to connections, first I'm going to define something called the vertical subspace. So if we take some point in our in P, we define the vertical subspace at that point to be, well, we denote it V sub P for vertical, and this is the kernel of the derivative of the projection map at P. So recall that if you fix a point X in M, then if we look at the image of a fiber under this, well, we just get that point back. So essentially, pi is constant along each fiber, which means that if we want to look at the kernel of the derivative, essentially what this is saying is these are all the tangent vectors that are pointing along the fiber. So in kind of parallel to the fiber, in a sense. So I'll just draw another picture here. We have our total space P, our base manifold M, have 2 points here, and we have our fiber at each point. The vertical subspace at a certain point is essentially the tangent vectors that are pointing along the fiber, like this. So the vertical subspace is the one that kind of points vertically in this picture. So this tells us how to travel along the fibers. but we want to travel between the fibers. So we now need to figure out a way to travel, I guess, perpendicularly to the fiber. Now, unfortunately, if we don't have a metric, there's no distinguished choice, but we can choose, basically, a direction to be the horizontal direction, or the direction that goes in the other way. So if we choose such a direction, like this, at every point, what this essentially does is this connects our fibers together. And we call this the horizontal subspace because it goes horizontally at each point. So definition, a horizontal subspace at the point P is a subspace, which we will denote H sub P, of the tangent space at P, such that the tangent space splits into the vertical component and the horizontal component like this. So this is the way of saying we are going like, this is a way to define a perpendicular direction. Now, in general, there are actually infinitely many choices of a horizontal subspace at any given point, if we don't have any sort of other structure. If we make such a choice, in general, given P in P. Such a choice of horizontal subspace at each P in P is called an Arisman connection, or just a connection for short. Is an Ehresmann connection. If this connection is also G invariant, in the sense that if you take any horizontal subspace at a given point and you act on it by this right multiplication, which is just the group action, then you get exactly the horizontal subspace at that new point when that you get to under the group action. We call such a connection a principal connection. And these principal connections are quite important. So they're these connections that also preserve the G bundle structure as well. So just to finish off, I have two examples of connections. We're going to take the trivial G bundle, smooth G bundle, which goes from M cross G to M. So the projection here is, well, just the projection down onto the M component of this Cartesian product. It then follows that the vertical subspace at any given point, which is the kernel of this projection map, here is just the tangent space at the point G of the group, which hopefully makes sense. The fibers is homeomorphic to the group, or diffeomorphic to the group, I guess, in this sense. And we want to travel in the same direction as the fibers for the vertical space. So that is exactly the tangent space TGG. Now, notice that the vertical subspace is given to us by the structure of the bundle. We don't get to choose what the vertical subspace is. It is just given to us by this being a bundle and the projection map. Now, a choice of horizontal subspace would be some sort of subspace that splits the tangent space of the Cartesian product. So we want to find some sort of subspace such that we get this splitting here. Now, a natural choice is to set this to be equal to TPM, because there's this isomorphism canonically to the tangent space of the Cartesian product splitting into the tangent space of both spaces, essentially. And this choice at every point gives us a connection. In fact, it's also a principal connection. As if we act on such a subspace, well, by definition, this is TPM. And right multiplication here is a diffeomorphism. So we're going to get the entirety, oh, sorry, not a diffeomorphism, a linear isomorphism, because right multiplication is a diffeomorphism. We get the entire space, and by definition, this is exactly the horizontal subspace at PHG. Now, this has a special name, which I've seen before. It's called the Maurer-Cartan connection. Now, if anyone knows more about the Maurer-Cartan connection, I would be very interested, because I've only seen the name. To me, it seems like a very natural choice of connection. But it's obviously got a name, so it's obviously important in some other ways as well. Now, last example, I'm going to take some G bundle, some principal G bundle, and I'm going to equip P with a Riemannian metric. If we do that, now there is a natural way to split the tangent space. We obtain a connection by setting the horizontal space at a given point to be just the orthogonal complement of the vertical space. And this obviously splits. This is a connection. However, it's not necessarily a principal connection. It might not be G invariant. But if we insist that our metric itself is G invariant, in the sense that you're preserved under this right multiplication, then this will be a principal connection. Now, in general, we can't guarantee the existence of a G invariant metric. We can only do this we can only guarantee the existence if the group G is compact. And for this reason, we often assume when we're dealing with these Yang-Mills things that our group that acting on our principal bundle is compact. And that allows us to discuss G invariant metrics, which gives us a wide range of connections that we can choose by just changing the metric. Okay, that's it for my talk this week. So thank you.
Thank you for that, Max.
Thank you, Max.
Does anyone
Now,
have any?
if there's questions, they'll have to be fairly quick because I will have to race off after this to a tube.
Any quick questions for Max about his discussion?
The Morikawa form is the connection form. You're going to talk about that next time, Max? I guess?
That will be next week's.
I just did a Google search trying to see any definition of Morikawa connection. So certainly, when you have a principal connection, it defines the Morikawa form. So,
yes.
I'm not sure what the difference is between. Given such a form, you can get a horizontal is equivalent to giving the horizontal subspace.
Yes.
So, yeah, I didn't.
Indeed.
Very quickly, I didn't spot any significant difference between the definitions.
I think this can arise if you take a Lie group to be a principal G bundle over just a single point.
Yeah, sure, right.
I think something arises there if you take a connection.
Yep.
This connection.
Yeah. So you'll get onto it, but there's the Morikawa equations for the connection form is got an equivalence for a principal G for a group left invariant vector fields on the group. I think. Anyway, you'll do some of that next time, I guess.
Yes.
Max, I might jump in with a quick technical question if that's okay. Your definition of connection, I can't remember if you said this. Do you require that the choice of horizontal subspace varies smoothly with the point P?
I don't think I said this, and I think that's a very reasonable assumption to make. So I would say yes, you do need it to vary smoothly in some sense. Okay. Cool. If anyone else has any objections to that assumption, I think it's something that we should have. I don't think I said it though. Cool. All right, we'd better leave it there since Max needs to run off. So let's thank our speaker again. Awesome. We'll let you head off, Max, and I'll stop recording now. Okay.